This video is on section 6.2 notes, verifying trig identities. You'll also hear people sometimes saying that these are trig proofs, just ways that other textbooks say this or verbalize it. Your textbook tends to say verify the identity. Sometimes they say prove the identity, but they could use either way. So one thing that I wanted to say before I start going over different strategies to complete these proofs is that none of these strategies work 100% of the time. They're just common entry points to proving the trig identity. So they're great places to start if you don't know how to get started, and they're things that seem to often work, but that doesn't mean that they will work every single time. So if you haven't yet, go ahead and print out the trig identities resource page. You'll need this. You can see that the first half of the page should look familiar. We can see the reciprocal identities, the quotient identities, the even and odd identities, and the Pythagorean identities. You can even see these kind of alternate versions of sine squared plus cos squared equals 1 that I talked about in the end of the previous video, as well as the 2 that I went over at the beginning of the video. And then we have other identities we haven't learned yet. So for today, we're just going to be using the top half of this sheet, but it'll be really nice for you to have it in front of you. So I'd make sure to print that out before I start watching this video. So yesterday, before we were even doing proofs, before we were verifying identities, you were just given an expression. So there was no equal sign in the problem. There was just an expression, and it just said to simplify the expression. And we used a couple of these strategies as we went through and we simplified the expression. So some of what I'm going to go over today is going to feel a little bit redundant, and honestly, that's a good thing. So a couple of the strategies that we used yesterday as we were simplifying expressions is we were getting common denominators as we did the problems. We were writing the problems in terms of sine and cosine as we did them. And then we were kind of alternating in our work between doing something where we substituted a trig identity into the problem, and then we would do just some math. We would do some things that we knew mathematically you're allowed to do. We would add common terms together. We would combine like terms. We would get common denominators so we could combine two fractions together. We would reduce things if we could reduce them. We would do different things that we've learned in math that we're allowed to do. And then maybe we would have to do another trig substitution. And so that's going to be kind of the flow with these problems, is that we're going to do something with trig, some sort of substitution, and we're going to do the substitution based off of our resource page. And then we're going to come back and we'll be doing some math simplifying. And we'll kind of go back and forth until we can show or prove the other side of the equation. All right, so these are nice. These are better than what we saw in section 6.1 because here we already know what the answer is. We just have to get there. Okay, so it says verify that the following equation is an identity, and we know that an identity is a mathematical equation in trig that is always true regardless of the angle value used. It doesn't matter what angle you plug in, it's going to be true every single time. So the first strategy, and this is one that works like 99.9% of the time, I pretty much always do this, is to work with the complicated side. So if I compare the left side versus the right side, the left side looks more complicated just because it's longer. It's got more trig functions in it. And so this is the side that I'm going to manipulate. It's the side that I'm going to put substitutions into, and it's the side that I'm going to do my mathematical simplifications to. So I'm going to start off just by looking here at the secant and the sine and the tangent, and I'm going to actually use one of my other strategies as well, which is to put things in terms of sine and cosine. And so I'm going to write 1 plus, and instead of secant, I'm going to write 1 over cos. And then I'm going to keep the sine. And then I'm going to rewrite tan as sine over cos. And this is equal to secant squared. So I'm not going to adjust anything about the secant squared side. This is what I'm proving. I'm proving that all of this is equivalent to secant squared. So next, I'm going to do just some math. I'm going to multiply these three things together. I'll put sine over 1. So I'm multiplying these three fractions. I get 1 plus 1 times sine is sine squared. Cos times 1 times cos is cos squared. And at this point, I have two options. I can do something mathematically. So I could maybe take these two and maybe get a common denominator. Maybe write this one as a fraction, get a common denominator so I can put these two terms together. Or I could do a trig substitution. And both of them work, to be honest. They're two different ways of doing the problem, and I'll get the right answer no matter what I do. But I'm going to go ahead and I'm going to take this and write it as tangent because I know sine over cos is tangent. And so that means that sine squared over cos squared is tangent squared. It would be sine over cos times sine over cos. So I'm going to say this is 1 plus tangent squared equals secant squared. Okay, and now from here, my options are always I can either do something in math or I can do some sort of trig substitution. Mathematically, I can't really add two things together like this. They're not like terms, and so I'm going to think about a trig substitution I could do. And if I look here, I can see that 1 plus tangent squared is equivalent to secant squared. And so I'm going to take the 1 plus tan squared out, and I'm going to replace it with secant squared. And I have officially solved the proof. I have shown that the left side of the equation is equivalent to secant squared. The right side of the equation was already equivalent to secant squared. And so I'm done. I completed the proof, or I verified the identity. All right. Another strategy is to multiply by the conjugate. And I'll explain more about what a conjugate is when I get there. So here, these sides, if you look, there's not really one side that's more complicated than the other. The two sides have like a little bit of like symmetry about them, you know, they're kind of the same. So when you're working with these, you could do either side. I would prefer to work with the left side because if you compare the numerator versus the denominator, I would rather fix a denominator that's gross than fix a numerator that's gross. I'd rather get rid of a gross denominator, okay? So that's kind of just my personal preference. It is a personal preference I've developed from doing problems like these, though, so I would probably trust it if I was you. So in this case, I'd say the left side is probably a little bit more complicated. So I'm going to work with the left side. I'm going to leave the right side alone. That means that I'm going to make the left side look like the right side to prove that the identity is true. So I'm going to start off with cos alpha over 1 minus sine alpha. And I'm going to multiply the left side by the conjugate. And the conjugate is just the same as the bottom with the opposite sign in the middle. So I'm going to multiply by 1 plus sine alpha on top and 1 plus sine alpha on bottom. And that's the important thing, is that you have to do exactly the same as what's on the bottom, but opposite signs. That's important. And then on the right side, I'm not going to change anything about the problem. I'm just going to copy it down. Okay, now for the top, I'm going to write this as 1 plus sine alpha times cos, and I am not going to distribute cos. And the reason I'm not going to distribute the cos is because if I look over at my answer, I can see that 1 plus sine is in my answer. Like, I want that to look exactly this way, and so I'm not going to distribute because I don't want to mess that up. So I'm going to leave 1 plus sine alpha and then cos alpha. Somehow this cos alpha is going to go away, and this is going to be the only thing left over. That's how we're going to get it to match the right side. Now in the denominator, I have 1 plus sine alpha and 1 minus sine alpha, and these two things have to be FOILed together. So I'm going to FOIL them off to the side. 1 plus sine alpha, 1 minus sine alpha. So I have 1 times 1 is 1. 1 times negative sign is negative sign. Positive sign times 1 is positive sign. And then positive sign times negative sign is negative sign squared. So these cancel, and I'm left with 1 minus sine squared. Okay, so that's the bottom. 1 minus sine squared alpha. Okay, and then the right side is still the same thing. 1 plus sine alpha over cos alpha. Okay. All right, next, if I'm looking at my answers over here, I know that somehow the only thing that's left on the top is 1 plus sine alpha. Somehow I'm going to have a cos alpha on the bottom, and right now all that I have on the bottom is 1 minus sine squared. So I have two kind of clues here that are happening. I know I'm probably not doing a mathematical step next because there's nothing that I could cancel out or reduce that could make this happen. But also because if I look over at my identities, I can see a squared, which tells me to look at my Pythagorean identities. And then I can see over here that the only way to take a sine and turn it into a cos is by using those Pythagorean identities. So for all of the things that we've learned how to do so far, sine and cos don't go back and forth with the reciprocal identities. They don't go back and forth with the even and odds. So the only thing that would help me convert from this sine into the cos that I can see in the final answer is my Pythagorean identities. So I can see 1 minus sine squared is equivalent to cos squared. So I'm going to trade that out. I'm going to make that substitution. All right. Now I'm not going to touch these parentheses because they're in the final answer, but if I look over here, there's some math simplifying I can do. I have cos on top and I have cos on the bottom, cos squared, cos times itself. So I can cancel one of the coses on the bottom with one of the coses on the top, and that leaves a cos behind. So this was cos squared on the bottom. I reduced one of them with the cos on the top. And that leaves me with 1 plus sine over cos equals 1 plus sine over cos. And so I have verified this identity. I've proved that the left side and the right side are the same. All right, next page. The next strategy that we're officially going over, but we've gone over it before, is getting a common denominator. So here we can see that we're going to be working with the right side. I'm definitely doing that because this right side is more complicated than the left side. And so I'm going to just copy down the left side. I won't be changing anything about that. And then on the right side, I'm going to copy these down, but I'm going to kind of space them out because I want to leave enough room, minus, to get a common denominator. Okay, so cosecant x minus 1, cosecant x plus 1. To get the common denominator, I'm going to multiply the first one by cosecant x plus 1 over cosecant x plus 1. I'm going to multiply the second fraction by cosecant x minus 1 over cosecant x minus 1. Okay, so the left side stays the same. And my first fraction is cosecant x plus 1 over whatever the denominator happens to be. My second fraction is going to be cosecant x minus 1 over whatever the denominator happens to be. And I'm going to go ahead and do the work off to the side for finding cosecant x plus 1 foiled with cosecant x minus 1. So I have to multiply those together. So cosecant times cosecant is cosecant squared. Cosecant times negative 1 is negative cosecant. 1 times cosecant is positive cosecant. And then negative 1 and positive 1 multiplied gives me negative 1. So this is cosecant squared minus 1. And so this is the denominator for each of those fractions. So I have cosecant squared minus 1, cosecant squared minus 1. Okay, so now I have a common denominator for my two fractions. I'm going to go ahead and write them together as one fraction. So I have cosecant x plus 1 minus cosecant x minus negative 1. Minus cosecant x minus negative 1. Okay, so the cosecants are going to cancel out. And positive 1 minus negative 1. Minus minus makes a plus. So 1 plus 1 is 2. Okay, so now on the right side, the denominator has a squared in it, and I'm at the point where I don't really have anything mathematical that I can do anymore. I was doing all these mathematical steps up here. I was getting my common denominator, I was distributing the negative, I was combining like terms, but at this point, there's nothing I can do that's really mathematical anymore, so I'm going to go back to thinking about if there's a substitution I could make with my trig identities. So since I see a squared here, I'm going to look at my Pythagorean identities. Cosecant squared is 1 plus cotangent squared. I know that these can be manipulated kind of like I manipulated this one. So I'm going to write another version of this. I'm going to subtract the 1 over, and I know that cosecant squared minus 1 is equivalent to cotangent squared. That would be an alternate form. And so I can go ahead and make that substitution. I can take the cosecant squared minus 1 and replace it with cotangent squared. So this is 2 over cotangent squared. And now at this last step, I have 2 over cotangent squared. I know that 1 over cotangent squared is tan. So I have 1 over cotangent, another 1 over cotangent. That's how I got it squared. That means that 1 over cotangent squared must be the same as tangent squared. And so I'm actually finished. 2 tan squared equals 2 tan squared. And so I've completed the proof. All right, last strategy. We've already talked about it. We're just going to apply it to this problem. So this last strategy is to write the problem, the side that we're going to work with, in terms of sine and cosine. So I'm going to take this and we're just going to write everything in terms of sine and cosine, and then we're going to go from there. So the reason I'm working with the left side is, again, because it's the more complicated side. And so cosecant I'm going to write as 1 over sine minus sine divided by sine equals cotangent squared. Okay, Now I have a fraction and a non-fraction, so I'm going to take this one, I'm going to write it as a fraction. So right now I'm not making trig substitutions, I'm just doing mathematically what I know is appropriate. So I have two fractions, I want to put them together, and so that means I need a common denominator between those two fractions. One of my denominators is sine, the other denominator is 1, and so both of these would have to have a denominator of sine for me to be able to combine them. So I'm going to multiply the second fraction by sine over sine. All right, so, and I haven't touched the bottom of the fraction yet, the bottom of the quotient, I guess. So I've got 1 over sine for the first fraction, I've got sine squared over sine for the second fraction, and then that whole thing is being divided by sine equals cotangent squared. Okay? Now I'm going to go ahead and put those two fractions together with their common denominator. So I have 1 minus sine squared over sine, and then that's being divided by sine. Now, when I have a fraction over something, I prefer for it to be a fraction over a fraction. It's just easier for me to deal with. And so I'm going to put this over 1 so I can think of it as a fraction over a fraction. And what I'm going to do now is I'm going to take this fraction and I'm going to multiply it by the reciprocal of the bottom fraction. So I'm going to have, I'll write it up here, 1 minus sine squared over sine times 1 over sine. And I want you guys to notice that I have not done any trig substitution since the beginning. So I have just been doing mathematically appropriate steps. I'm getting a common denominator. I'm writing this, now that I have a common denominator, as one fraction. I wrote this as a fraction so that I could keep the first fraction, change it to a multiplication problem, and multiply by the reciprocal. All right, so at this point, I'm going to multiply my fractions together. I have 1 minus sine squared times 1, which gives me 1 minus sine squared. On the bottom, I have sine times sine, which is sine squared. And if I have squareds, that means I'm probably looking at a Pythagorean identity. So I'm going to go back and look at my page, and I can see that 1 minus sine squared is cos squared. So I'm going to replace it with cos squared. And part of the reason that I'm doing that, taking this out and replacing it with cos squared, is that I know what the final answer is. I know that I have to make the right side equivalent to the left side, and I know that cotangent is cos over sine. So I know that it's beneficial for me to get this. So now I've got cos squared over sine squared. And if cos over sine is cotangent, then cos squared over sine squared is cotangent squared. And so I finished my proof. All right, I wanted to give a couple warnings to you. One is to only work on one side of the trig identity, and this is a little bit against what your textbook does, because your textbook actually has an example where it says one strategy is to work on both sides. But I have always heard to only work on one side, and when I Googled it, when I did some internet research, once I read the textbook, it kind of confirmed that generally speaking, most people say you're not supposed to do that. You're only supposed to work on one side. So when you complete a proof, you should mess with one side and show that that one side can equal the other side. right? Second is after you use a trig strategy, use real math to simplify. And I said this throughout the video, but the thing I want you to be careful of is making up math and having wishful thinking and kind of forcing it because you know what the answer is supposed to be. So this is the unit, this is the type of lesson where I usually start to see students show some crazy stuff that's not actually true because they're trying to force it. There's always correct math that will get you to the final answer. So that's one thing I want you to keep in mind, is that whatever math you use to simplify has to be real math. It has to be math that would work if you were using numbers and not trig functions. So be careful of that. Now, one other thing I wanted to point out to you guys is that when you do these problems, there's usually some ways to do them that's a little bit easier and some ways to do them that are a little bit more difficult. And it just depends on how you approach the problem. So I'm going to show you, and don't be mad at me, but I'm going to show you how the textbook wanted you to do this last example. So this is how the textbook did the last example. They did not have you turn the problem into sine and cosine. They had you take the problem and split it into two separate fractions and work with the problem that way. And then they ended up using a reciprocal identity and then a Pythagorean identity. And the reason I did not have you do the problem this way is because in my experience teaching this, my students tend to approach every problem by turning it into sine and cosine. That's a method that students like. They end up doing it often. And so what I wanted to do is I wanted to give you an example problem that would kind of have a flow to it that seems to happen often. This is a flow and a proof that I see a lot. I see this type of thing getting a common denominator and running into 1 minus sine squared is a Pythagorean identity that I can change to cos squared. So this is a great example problem because you'll probably see these steps in this order again on a similar problem. But the reason I wanted to show it to you is because there are two different approaches to this problem that look drastically different but still prove it. And that's how all of these problems are. There's usually multiple ways to do the problems and still get the answer right. Okay, so keep that in mind. As you're going through and practicing these problems, the problems that you'll be doing on the MyMathLab platform are multiple choice answer, or they give you a drop-down box and they kind of force you into the solution method they think you should be doing. So I'll be assigning some problems on MyMathLab for you to do. And then I'm going to assign some problems in the textbook for you to do so that it's completely just a blank sheet of paper. You have no help. You have to do it completely on your own. Without getting some extra support from the people who created the MyMathLab problems. So you're going to be doing both of those. All right. If you are struggling on these problems, make sure that you try them before the deadline, before Sunday night, so that if you need to reach out and ask questions, you can do so before you need to turn your work in.